Now, just how do light rays act to form a clear picture within the eye? First, let us realize that light rays reflected from any object radiate in all directions, and that as an object moves farther away from us, the angle between the rays that enter our eyes grows smaller and smaller. And finally, when the object has reached a distance of 15 feet or more, the rays entering our eyes are practically parallel. Now, nature has provided that parallel rays shall produce a sharp image upon the retina without any effort, and, as one may say, with the eye in a state of complete relaxation. But if a distant object approaches the eye, the angle between entering rays again grows larger. This increasing angle changes the direction of the light rays as they pass through the lens, so that the sharp image falls behind the retina. As a result, the image upon the retina tends to become blurred. This blurring causes a response or reflex within our brain, which brings about harmonious internal adjustments of all parts of the eye. This adjustment is called accommodation. Accommodation restores the sharply focused image with marvelous speed and accuracy. This is all the more remarkable because the distance between lens and retina is fixed, and the lens itself must change its shape. Now compare this with the focal adjustment of a camera. Here the lens remains unchanged, but the film itself is moved until it reaches a sharp focal image. It is also necessary that both our eyes be fixed upon the same point in order that we may see an object clearly. Thus, as an object approaches us from a distance, our eyeballs turn accordingly. This movement is called the convergence of visual axes. This action is shown here as the object approaches and recedes. Here, in addition, we see the lenses accommodating their optical shape under the combined influence of blurred image and eyeball movement. And now let us look at this highly enlarged view of the lens itself. It has a soft, yielding body and is as transparent as glass. But it also has a firm, ball-shaped central core or nucleus. It is contained within a thin, elastic membrane and is suspended all around by a spoke-like arrangement of delicate threads or ligaments. The lens itself lies between two liquids. These liquids can exert pressure. All liquids cannot be compressed. You may ask then, how is this soft, pliable body of the lens made to take on the different degrees of convexity necessary for accommodation? In order to explain this, let us again call attention to the important ciliary muscle, which we see here in the diagram. This muscle is shaped like a broad ring which can expand and contract. Whenever it does contract, it must press upon the non-elastic vitreous humor. This liquid is confined within the rigid capsule of the eyeball and must, therefore, exert pressure upon the lens. Now, the lens as a whole cannot give way against the equally non-elastic aqueous humor and its confining cornea. So the only part which can possibly yield to the pressure of the vitreous humor or body is the soft substance of the lens. This lens substance is thus molded into an even curve against the rigid ball-shaped core, thus forming this highly convex bulge which science has called lenticonus. So whenever the image upon the retina becomes blurred, the brain automatically causes the ciliary muscle to contract or to relax until the lens has attained just the right shape to restore a sharply defined image upon the retina.